Hello everyone. In this video, I'm going to talk about the equation of motion in vector format. Okay, last video I introduced the component representation of a vector, and I show you the vector form of the position vector, velocity vector, and acceleration vector. And during the derivative, I say the unit vector, which point shows the direction. Okay, the unit vector is stationary in our derivation because when it's intuitive, the coordinate is independent of time. But in fact, in very difficult problem, we don't want the coordinate is independent of time. And here I show you an example. It's called moving frame. Especially if you do the curved space or rotational motion, you want your coordinate is a function of time. It's better to describe problem, especially difficult problem in that way. So let me show you the animation. Okay, you can see your coordinate can also be function of time. But in our course, we just treat it very simple problem. So our coordinate is fixed, but I'll show you. You see, it's a beautiful animation. You see your coordinate, your direction is changing, so your coordinate is a function of time. Show you one more time. There's a blue color, red color, and black color. These are three unit vectors, and follow the trajectory. You will see these three unit vectors. Their direction depends on the time. Okay. Yeah, for difficult part, like I say, for difficult problem, you want your coordinate is a function of time. But in this class, we won't face such problem. Okay, just show you. So and what's this video I'm talking about the equation of motion in vector format. Okay, so let's just like I said, in more than one dimension, 2-dimension and 3-dimension problem, last time I just used the equation to show you really can treat the motion independently. For example, it's 2D motion, you can treat the X component independently and treat the Y component independently. Okay, and today I just show you it's in the vector form, you really can do that. Okay, and in 1D kinematics, I have two equations of motion, right? The two I most like. Okay, that the where I should draw. I should write down this. Okay, I just use a blank slide. Okay, last time or in 1D kinematic problem, there's equation motion I very like. Final velocity is equal to initial velocity times acceleration plus acceleration times t. And of course, right now we are doing constant acceleration motion. Yeah, we don't want to. Let's just make it simple, right? And one final position is equal to initial position plus initial velocity times t time plus 1/2 at squared. So this is a 1D kinematics problem. So in many dimensions, in vector format, okay, what will be what the equation motion looks like? It will show like this in many textbook. Okay, so vector, I use the arrow to represent the vector, and it's constant acceleration. So okay, still t, and then the position in 2 and 3 dimension, the position vector, I use r. Okay, maybe r is better. The final position is equal to initial position plus initial position vector format times t plus 1/2 a times t squared. This is in vector format, right? Looks important. And Just put a vector on this quantity. Okay, put a vector on this quantity, velocity, position, and acceleration. Okay, so it's the vector format. But what we like to do is want to I want to address is in real calculation we rarely use the vector format. We use a component. We use a component language more often. ANGU. Okay, because component language is much easier for calculation. Using a vector form to do the calculation, it's very difficult. So in component language, what will be will the equation of motion looks like? And we just use two-dimensional motion as an example because it really can extend to three dimensions. So what it looks like? Okay, so for this one, for the velocity, it will look like this. Okay, thus you have treated independently. If I want to final state and x component, okay, x component equal to initial velocity x component plus a acceleration vector x component of x vector times t. And be careful. Okay, we can treat the motion independently. Okay, just like a vector, we can treat a vector independent each component. Treat independently. So be careful for this. So similarly, we do the same thing on y component, initial velocity y component, and initial acceleration at y component times c. Okay, treat the motion independently. And so for this one, another equation motion I like. Let's only show two dimension x and y. Okay, final state equals initial state plus v initial state, but x component times t plus y 1/2 a x component and t square, and y component is this initial velocity at y component times t plus 1/2 acceleration y component t square. Yeah, you just treat component by component, and these two equation of motion can solve lots of things. These two equation of motion can solve lots of problems. That's all you need about for the 2D kinematics. And for 3D, just add one another component. But in this class, we rarely treat the 3D motion. Most of the time, it's 2D motion. In 2D motion, these two equations is enough. Okay, it's really enough. Okay. Okay. So I will quickly use a simple example to demonstrate how to use the equation of motion component by component. We use a very simple example on textbook. Wait for me. And okay. And the example is on, I think I have on this slide. Yeah. Okay. This problem, okay, example 3.3 on textbook. And this problem is like there's a boat and who has initial velocity to the x direction. Okay, its speed is which color? Its speed is velocity is 7.3 meter per second, and plus x direction. Okay, plus x direction, and then suddenly he felt an acceleration. Okay, and the acceleration he gave an acceleration. The acceleration is 60 degree with respect to the x horizontal axis. Okay, and he give the magnitude of acceleration. He give magnitude of acceleration is 0.28 meter per second square. Okay. Okay, that's the initial condition. What else do we have? Yeah, that's pretty much the setup of this problem. You say, and he want to ask after, let's see, after the wind struck, the acceleration struck, or the force or acceleration strike the boat for 8.7 seconds. Okay, what's the travel distance? What's the travel distance? Travel distance of the boat. Distance of the boat. Okay. Okay. Boat is here, and it suddenly give acceleration in this direction, and then he want to ask after 8.2 seconds, what's the displacement? I think displacement would be in this way, right? Okay. You say what's the displacement? Oh no, sorry, not displacement. What's the travel distance after 8.8 seconds? Okay, so for this problem, it's 2D kinematics problem and 2D kinematics problem. Yeah, I just write down the equation of motion on x direction and y direction. Okay, so x direction is xi equal to xf plus v initial velocity x component times t plus 1 over 2 ax times t square yi equal to yf plus v initial velocity y component times ty over 2 ay t square. That's the equation of motion I like. Okay, and in this problem, we set up the coordinate. Let's say the origin is here. Let's say the origin is here. Okay, you can pretty much answer the problem. Okay. And so, for this problem, the initial position he is here. So the initial position in x component and y component are all 0. xi equal to 0 and yi equal to 0. Okay. And what's the x component for the velocity at the initial state? Okay, initial state is the initial velocity of the boat is 7.3 and plus x direction. So where should I write this down? Okay, right here. Initial x component is 7.3. And at the same time, it only has x direction and the initial state. So initial state, the y component is 0. Okay, so and the next one is the acceleration of x component. Acceleration x component, I think it's the magnitude of acceleration times cosine theta. Okay, and give the acceleration magnitude is 0.82. Okay, so it's 0.82 times cosine 60 degree. Okay, at the same time, what's the acceleration as y component is magnitude of a times sine theta. So 0.28 times sine 60 degree. So what the value? One is 0.41. You can calculate by yourself. I just write the answer down. Okay. So I think it's pretty much we have, yeah, I think that's we pretty much get all the information. So he want the the travel distance of the travel distance after at 2.8 sec after 2.8, so 8.7. Yeah, I keep saying 2.7. Okay, 8.7 seconds. So t is 8.7 seconds. So okay. So let's see. Sorry. Equation I've been wrong here. Thankfully, I didn't write just the symbol wrong. Final. I. So, okay, let's do the calculation. What's the XF? Okay, XF this is 0, so this is the VIX is 7.3. 8.7 seconds plus 1 over 2. 0.41 and 8.7 seconds squared. And your final position of y is initial is 0, and initial velocity y component is also 0, so this is 0, so it's only have 1 over 2, 0.71, and the 8.7 square. Okay, what's the value? It's, I think one is 7 point, so xf is 79.03, and yf is 26.87. You can use your calculator to check the answer. Okay, so x is x. So the displacement is the travel. The displacement can be composed in 2 dimensions, and x component is about 79 meter, and y is about 27 meter. So the displacement, I think, is in this direction. So the distance, the travel distance should be 7.03 square plus 26.87 square, and then make a square root. I think it's not hard for each of you. Then the final travel distance is 3.7 meter. Okay, so that's the answer. The distance is 83.47 meters. Okay, and then for this problem, you can also check VF and VI. Okay, check yourself. Okay, I think it's not hard. Okay, because just write the equation of motion again, velocity is equation of motion again. And you have acceleration, you have time, you can solve everything. Okay, so this video it just show you how to use the equation of motion, two-dimensional equation of motion, and treat the motion independently. You can solve lots of problems. Okay, in the next video, I'm going to talk about the projectile motion. Okay, and this probably another famous example of two-dimension motion. Okay, so see you in next video. Bye bye. Bye bye.